You ever look up at the sun and just wonder, how does it do that? Well, today we're going to crack open one of the oldest and biggest questions in science. What is the secret engine that's powering our star? For most of human history, the sun was just there. It was this big, bright thing in the sky, and that was that. But then, once we started applying physics to it, we ran into a huge problem. A massive mystery, really. How in the world has it been shining for so long? So before we get to the actual answer, I think it's really fascinating to look at the ideas people came up with first. I mean, they were totally logical, but as you're about to see, the sun is just way more extreme than anyone could have possibly imagined. Okay, so the most obvious guess, right? It's just on fire, it's hot, it's bright. It's got to be burning something. Maybe it's like a giant lump of cosmic coal. Makes sense. But when you actually do the math on that idea, well, it turns out that even if the sun were made of the absolute best chemical fuel we know of, it would burn out in only about 10,000 years. Yeah, that sounds like a long time to us, but on a cosmic scale, that's nothing. It's the blink of an eye. And that's where the idea completely falls apart. See, by the 19th century, geologists already had solid proof that the Earth was way, way older than that. We're talking hundreds of millions, maybe even billions of years old. So a 10,000-year-old sun? No way, it just didn't add up. So it was back to the drawing board. All right, so theory number 2. This one's a lot more clever. It came from two brilliant physicists, Kelvin and Helmholtz. Their idea was this. What if the sun is shining because it's slowly collapsing under its own massive gravity? All that gravitational energy would get converted into heat. And you know what? This idea worked a lot better. This process, which we now call the Kelvin-Helmholtz mechanism, could actually keep the sun going for about 25 million years. That's a huge improvement. For a little while there, it really seemed like they'd cracked it. But you guessed it, those pesky geologists and later the discovery of radioactive dating proved that even 25 million years was just not enough time. The Earth is billions of years old, which means the sun has to be too. So they needed to find a new energy source, something radically, unbelievably powerful. And to find that source, we have to go on a journey. We have to stop looking at the sun from way out here and actually dive deep inside it, peeling back its layers one by one until we get to the incredible engine right at its center. So our trip begins in the corona. This is the sun's ghostly outer atmosphere, the part you can only see during a total solar eclipse. And right away, we hit a total mind-bender of a puzzle. It's over 1,000,000 degrees Kelvin out here. How is it hundreds of times hotter than the actual surface of the sun down below? It makes no sense. Okay, let's keep going. We're dropping down through the chromosphere now. It's this messy, reddish layer where the temperature cools down to a modest 10,000 Kelvin. And here we are, at what we would call the surface, the photosphere. This bubbling, roiling layer of gas is the point where light is finally able to break free and travel out into space. This is the light we see back on Earth. Okay, hold on, we're diving beneath the surface. Now we're in the convection zone. Just imagine a giant pot of boiling water. That's literally what's happening here. Huge blobs of hot plasma rise up, release their energy, cool down, and then sink again. It's this constant, violent churning. Going deeper still, we hit the radiation zone, and the density here is just insane. It's so packed that a single particle of light, a photon, can get trapped in here for more than 100,000 years, just bouncing around from atom to atom like a pinball before it finally gets out. All right, after that epic journey through all those layers, we finally made it. We are at our destination, the very heart of the sun. This is where the secret is finally revealed. Welcome to the core. The conditions here are almost unimaginable. We're talking 15 million degrees Kelvin, and the pressure? Over 250 billion times the air pressure on Earth. It's only in these extreme, violent conditions that you can unlock the most powerful energy source in the universe, nuclear fusion. Now, this is a super important point. The nuclear power plants we have on Earth, they use fission. That's where you split big, heavy atoms apart. The sun does the complete opposite. It uses fusion. It takes tiny light atoms and smashes them together.
This whole process is called the proton-proton chain, and here's how it works. You take 4 hydrogen atoms, just protons really, and you slam them together so hard that they fuse and become one helium atom. But here's the crazy part, the magic trick. The new helium atom actually weighs a tiny bit less than the 4 hydrogens that went into it, about 0.7% less. So where'd that mass go? It's not lost, it gets converted directly into a massive amount of pure energy. You've heard of E equals mc squared? This is it, in action. So you might be thinking, okay, if it's doing all this fusion, why doesn't the sun just explode like a giant hydrogen bomb? Well, it's because it has this perfect built-in thermostat. If the fusion rate gets too high, the core heats up and expands. That expansion cools it down, which slows the fusion. If the fusion rate drops too low, the core contracts, heats up, and that boosts the fusion rate again. It's this beautifully stable, self-regulating system. Okay, so this colossal engine buried deep inside the sun, it doesn't just sit there quietly. Nope. It creates what we call solar weather. And we're talking about really dramatic, beautiful events that can affect the entire solar system, including us. All of this wild activity, everything from those cooler, dark patches we call sunspots to these incredible, violent eruptions of solar flares and prominences, it's all driven by the sun's insanely powerful magnetic field. It gets all twisted up and tangled by that churning plasma we talked about earlier. And here's something cool. This weather isn't random at all. It actually follows a pretty regular pattern. It builds up to what we call a solar maximum, then it dies down to a solar minimum, all over a very predictable 11-year cycle. So why should we care about all this, being 93 million miles away? Well, because when a big solar storm hits, the sun can shoot these huge clouds of charged particles right at us. And those particles can mess things up. They can disrupt power grids, disable satellites. But on the bright side, they're also what give us those absolutely beautiful auroras, the northern and southern lights. And there you have it. We started with such a simple question. Why does the sun shine? And that question took us on a journey past old, busted theories, down through layer after layer of superheated plasma, until we found it, a nuclear furnace at the heart of our star, burning steadily for billions of years. It really makes you wonder, doesn't it? If this is the engine running our pretty ordinary average star, what other incredible secrets are hiding inside the billions of other stars scattered across our galaxy?